Hello, and thank you for watching our presentation. Our group is the Multipurpose Motorcycle Trailer, or MPMT. I am Tony Hester. My fellow group members are Logan Street, William Dow, and Kyle Guggenheim. So what is an MPMT? It is a trailer that can be pulled behind a motorcycle with the following capabilities. It can be used as enclosed dry storage, open-top pet carrier, a flatbed trailer, and it can be pulled with most tow-capable vehicles. As shown, our dog loves riding with my wife and I, but we now have two dogs and no way to ride with both of them. During research, I could not find any products that matched what I was looking for. Products found were either bulky or made completely out of fiberglass and would provide no protection to the pets in case of an accident. Because of this, we thought it would be good to design our own trailer. The trailer will be used in Ohio, so we will use Ohio trailer rules and regulations for trailer use. You can pause the video to read the individual laws and regulations if you would like. To develop our timeline, we began by creating a step-by-step plan, and then using Microsoft Project, created a Gantt chart. Here is an overview of our timeline. We applied for funding through the Arm and Fleck grant and were approved for $4,000. Our original design left us with an $816 deficit. Part of this deficit was due to using 1/8-inch aluminum plating that would be welded to the cage. This would have cost $1,660. Because of this, we decided to switch to using 20-gauge aluminum sheeting and applying it ourselves. As seen, we came in under budget, around $3,300. We designed a scaled trailer model that was modeled to be a replica of the actual trailer, and this was done inside Autodesk Inventor. The structural cage was designed using Autodesk Inventor's cage design feature. The aluminum panels were designed within Autodesk Inventor as well, using the sheet metal design feature. As shown, our original design was very simple. The second design is more aerodynamic and more visually appealing. After speaking with multiple welders, we realized how difficult and expensive it would have been to have this design manufactured. The next design was simplified into 3 tiers. As seen, each of the 3 colored tiers are comprised of simple angles. All of the more difficult angles can now be accomplished by connecting the 3 tiers. The next design removes unnecessary supports. Next, shows the cage with the aluminum sheeting, and the final image shows the entire pet enclosure on the trailer. The design has a skeletal cage that is comprised of 3/4-inch aluminum square tubing, 20-gauge aluminum sheeting. The cage can be easily attached and removed from the trailer by one person. A lid was designed so that we could use the trailer for dry storage, and a tailgate was designed to allow safe and sturdy loading of the animals. This video shows an animation of the exploded view involving all of the components of our design inside of Autodesk Inventor. Next, William will discuss the assembly process.
For the assembly process, the hitch was purchased and is specifically designed for a Yamaha V-Star 1100 motorcycle. The hitch was installed to the frame of the motorcycle. The ball hitch allowed the motorcycle to have a good amount of lean angle when turning. A standalone wiring harness kit was connected to the motorcycle to use the trailer light during normal operations. For the trailer assembly, we purchased a 40 by 48-inch pre-built aluminum trailer kit from Northern Tool Equipment. The trailer kit came with reflector, running lights, license plate lights, signal light, brake lights, and wiring harness. We soldered the wiring harness for the light, heat shrink wrapped them, and securely tightened them to the trailer frame. We put a 3/4-inch thick wear-resistant plywood on top of the trailer to use as the trailer base. Moving on to the cage frame assembly. The cage fabrication was outsourced to CG Weld for welding using 3/4-inch square aluminum tubing. Additional 3/4 inch aluminum flat bar were added to the cage to provide more support for the aluminum panels. We added total 4 of 1.5 inch square tab to the bottom of the cage for securely bolt down the cage to the trailer baseboard. Moving on to the panel assembly. The first attempt of making the panel template was using cardboard to form around the cage frame. This was a failure because the cardboard was very flexible, but we did learn a lot during the process. The final attempt of making the panel template was using poster board instead of cardboard. This gave us a more accurate fit and dimension of panels. We then traced the template on a 20 gauge aluminum sheet for cutting. We used electrical sheet metal shears and aviation snip to cut the aluminum panels. The panels were formed using metal bricks, shaping hammers, and rubber dead blow hammers. The panel then securely attached to the cage using stainless steel sheet metal screw. As you can see in the slide, we have the photos of the panel assembly from start to finish. Feel free to pause the video if you need to take a closer look at the process. Moving on to the lid assembly. We made a lid to bolt on top of the case via a rift nut, so we can use the trailer for dry storage. The lid was made from a 1/4 inch thick polycarbonate sheets. For the door assembly, the door frame was also welded by CG Weld using 3/4 inch square aluminum tubing. The outer door panel was installed with 20 gauge aluminum sheet using self-tapping screw. The inner door panel was riveted with an 8-inch thick polycarbonate sheet, and we glued a rubber padding on top to provide better traction on the surface. The door was attached to the case frame using a heavy-duty P&O hinge. We used 2 stainless steel wire cable to hold the door as a tailgate, and 2 latch locks were used to lock the door in place. Here are some images of the working process on the door assembly. Moving on to the weather sealing. A 1/4 inch thick rubber strip was used to seal up the gap between the door and the cage. Additional seal was added as well to ensure watertight seal between the door, the lid, and the cage. To seal up the gap between the panels, we used all-weather resistant silicone on the inside of the trailer. Moving on to the padding and protection. We used a 3/4 inch thick soft rubber foam mat on top of the trailer base to have some cushion protection for the dogs. A thick foam pipe insulation was used to wrap around the top of the frame to give the protection for the dog head and neck. The dog will be securely attached with a leash and will be tightened down to the base of the trailer. This will prevent the dog from able to jump out of the trailer when moving. This way the dog will be safe and be able to lay down if they needed to. Here are some images to give a closer look of the sealing and padding protection. While we were testing the trailer under the bright sunlight, we found that the aluminum panels were very shiny. So we sent the trailer to Saint to paint, which makes it safer when pulling the trailer on the road. And overall, we just want to have a more finished look of the trailer.
Moving on to the analysis portion of our presentation, we conducted various forms of engineering analysis within our project. This includes a finite element analysis, a computational fluid dynamics analysis, and a wind tunnel analysis, with the purpose being that we wanted to gain a better understanding of the aerodynamics, drag and lift coefficients, drag and lift forces, and strengths and weaknesses of our design. In order to do this, we used ANSYS 2020 R2 for both the finite element analysis as well as the computational fluid dynamics, one using the static structural function, another one using the ANSYS Fluent. The wind tunnel that we utilized is the one that is located at the Miami University Middletown campus as well. The finite element analysis included a comparison between the static, loading, and increasing pressure acting on the entire cage structure. Within the FEA, our primary focus was on the cage design and testing its strengths and weaknesses through simulations. The static loading focused on having 10,000 pound force acting on individual components throughout the cage design, while the increasing pressure simulation had increasing pressure acting on the outside of the cage design that was increased with time. The range for this was 0 to 100,000 psi. In the following video, we are showcasing the increasing pressure simulation. As we can see, as the pressure is increased with time, we do have some deformation that does occur. Moving on now. For the computational fluid dynamics analysis for this project, we decided to conduct a symmetrical analysis using a simplified trailer model. We made the simplified trailer model using Autodesk Inventor, and then we refined the model using ANSYS Space Claim prior to conducting the analysis. The reason that we did a symmetrical analysis was in order to reduce the total computational time, since we were going to run multiple simulations. Within ANSYS Fluent, we made use of 2 physics models for comparison purposes to validate the results, as well as check for any discrepancies between them as we collected data. The models that we used include the K omega gecko, as well as the K epsilon with enhanced wall treatments and realization. The reason that we utilized these models is because both of these models are for turbulent flow. Since, as I mentioned previously, we conducted multiple simulations, and we did this to address various speeds in which the design will experience while it is in operation. These speeds include 5 miles per hour, 10 miles per hour, 15 miles per hour, 25 miles per hour, 35 miles per hour, and 45 miles per hour. Moving on now. In this table, we have the results that we collected from both the K omega gecko model as well as the K epsilon with enhanced wall treatments model. When we finished our simulations, we recorded these results and then tabulated them using Microsoft Excel. If you would like to review the results further, feel free to go ahead and pause the video now. Here we have some of the images that we captured from when we ran the 45 mile per hour K epsilon case. In the top left, we have the results for the drag coefficient as it was running through the 500 iterations that we were using for the simulation. As we can see, as we get closer and closer to 500, we reach a stability point, allowing us to know that our result has truly converged. On the right of that, we do have the drag force, and we can see that it also converges, giving us an accurate result. On the bottom left here, we actually have the turbulence model using the symmetry plane and the simplified trailer model. As you can see, we do have some turbulence that occurs in this case. And on the right side of it, we have the vector path streamlines using individual vectors to showcase how they are flowing over the simplified trailer model. Moving on now. In the following video, we're showcasing the 45 mile per hour K epsilon case again as well. What is shown here is a velocity streamline animation that was made using CFD Post. And as we can see, as the velocity streamlines move over the simplified trailer model, we do have a bit of turbulence that forms. We wanted to pursue this further and verify that our model was in fact getting and forming turbulence. And in order to do this, we decided that the best course of action was to conduct a wind tunnel analysis, which this will be discussed next.
To start the wind tunnel testing, we had to fix and modify the wind tunnel. The wind tunnel needed a new smoke machine, and the smoke inlet pipe needed to be modified for better smoke distribution. The wind tunnel testing was done using a 3D printed model of the MPMT at 1/12 scale. The wind tunnel testing gave us a better understanding of the aerodynamics in comparison to the CFD simulations. To better compare the wind tunnel testing to the CFD simulations, the 3D printed model was made from the same file and was tested at the same speeds of 15, 25, 35, and 45 miles per hour. An additional speed of 50 miles per hour was done to test the performance of the wind tunnel. In the video, we can clearly see the wind tunnel test a high turbulence directly behind the trailer. This can be compared to the CFD simulation where we see the same results. We can see a light disturbance in the airflow behind the trailer at 15 miles per hour. As the speed increases, we can see the disturbance become more intense. Once the trailer was assembled, we attached it to the motorcycle for testing. The testing points we were looking for was maneuverability, braking, and stability. The trailer tongue weight is 8.3 pounds, which is under our goal of 40 pounds. The total weight of the trailer is 263 pounds, which is under our goal of 402.5 pounds. Riding the motorcycle with the trailer felt light and simple to handle. Tony could not tell any difference in riding the motorcycle with the trailer behind him. When braking, Tony could not feel any difference with and without the trailer. Since the trailer is wider than the motorcycle, Tony noticed that he will have to maintain positional awareness of the trailer while riding on the street. Typically, motorcyclists ride in the left or right half of the lane. While pulling the trailer, he will have to stay closer to the center of the lane. To get the dogs more comfortable with the trailer, Tony started by training them to jump in and out of the trailer. Then to have the dogs ride in the trailer, Tony started by riding at very slow speeds with people close behind him for safety. The dogs seemed very nervous at first, but slowly became more comfortable riding in the trailer. The outcome of our project was a functional and safe design. The trailer is registered and safe for road use and follows Ohio state laws. The finished product is safe to be used behind a motorcycle and other tow-capable vehicles. For the future plans, more testing to address road performance and stability once road testing can be conducted. Potential continuation of CFD to compare more physics models and gain a better understanding for the aerodynamics of the design. Altered trailer frame to follow footprint of the cage. Addition of a windshield to protect the dogs during higher speeds. And axle-less suspension to improve ride quality. Here are references for the presentation. We thank you for your time and we hope you enjoyed the presentation.